Welcome to that of the competitive examination platform. Here we have described the GATE question solution 2025. This solution mainly solved the organic chemistry on the basis of the different textbooks and the knowledge of the organic chemistry. First question is that of the retrosynthetic problem. In this retrosynthetic problem, the target molecule has been synthesized by the different way. The right option for the synthesis of the target molecule is the B, and this can be explained as if we leave the carbonyl and C bond, then the positive charge is created on the carbonyl carbon and the negative charge created on the CH2 carbon, and this negative charge is not stabilized by any electron withdrawing group. But if we clicked on this CC bond, then the negative charge is created on the diethyl malonate carbon, and this diethyl malonate has been stabilized by the two electron withdrawing group and the positive charge. This is the synthon, and the corresponding synthetic equivalent is that of the alpha beta unsaturated carbonyl group, and this alpha beta unsaturated carbonyl compound easily react with this negative charge and produces the target molecules. Next problem is the spin splitting problem from that of the NMR spectroscopy. Here the deuterium atom is introduced in that of the toluene, and the two deuterium atom is taking part with that of the split with that of the HA. Here the HA is affected by the two deuterium atom with their spin number I equal to 1. According to the spin selection rule, spin splitting rule, 2Ni plus 1 means I equal to 1. So the number of lines equal to 5. So it is splitted as a quintet. And this similar type of the problem, this screenshot has been taken from that of the Pavia book, where the CHD2 functional group has been clipped by the deuterium as well as the hydrogen atom. In such cases, in 13C NMR, the hydrogen and deuterium is also splitted by the formula 2Ni plus 1. Summation of 2Ni plus 1 means if we here the deuterium has spin number I equal to 1, so it can be splitted as 2Ni plus 1 means the number of deuterium atom is 2, so it becomes 2 into 2 into 1 plus 1. And in case of the hydrogen, only one hydrogen atom present with their spin number half, and it multiply it, we get the total number of splitting equal to 10. This is the problem from that of the carbohydrate, where the disaccharide, a disaccharide X does not show mu rotation in aqueous solution. The definition of the mu rotation is the change of the specific rotation in aqueous medium, means one form is converted to another form through an open chain. Here, if the anomalic carbon is blocked by the oxygen atom, then there is no chance to form the monosaccharide in the presence of the aqueous medium. So, it cannot convert it to another open chain form. Hence, it is considered as the non-reducing sugar. Similarly, in case of the sucrose, a disaccharide X does not show mu rotation, means it does not show any mu rotation. So the mu rotation compound is that if it can open it, and it produces the aldehyde, and it gives that of the another open chain form. So the option is that a disaccharide X does not show mu rotation in aqueous solution. Acidic hydrolase of X, two different monosaccharide, means two different monosaccharide means here X produces the two different monosaccharide. Suppose in case of the sucrose, here the two monosaccharide it produces, one is the D-glucose, another is the D-fructose. This is the two different monosaccharide, and it does not show mu rotation, as it is cannot go to open chain form. but it also does not show mutation, but it produces the same aldehyde source, that is the D-glucose, after hydrolysis with the H3O plus. Similarly, it has anomeric group is 3, so it is open, it produces the open chain form, and so it shows mutation, so the option is not going at that, and it also shows mutation, so the option is not going with that. So the correct option is that of the sucrose, which does not gives the mutation, as well as it produces the two different monosaccharide after hydrolysis. Next is the mass fragmentation problem. In the mass fragmentation problem, it has been shown that the different type of the compound is given in the options, and the problem is that the more intense peak appear at 120 in EI mass spectrum, and this is the first option where the Maillard fatigue rearrangement will occur and produces the enol intermediate, and via the gamma hydrogen shift, and this gives the mass value 120. Similarly, this compound also shifted the gamma hydrogen atom and produces the same enol intermediate, and it also gives the mass value 120. But here the water is eliminated to give the ketene intermediate where the mass value is 134, but in case of the ester of the salicylic acid produces the mass value 124.20 after the elimination of the methanol. So the option A, B, D are the correct. Next is the oxidation problem, where the cyclohexene converted to the cyclohexanone. Here the cyclohexene first converted to the allylic bromine on treatment with the N-bromosuccinimide with that of the benzoyl peroxide, and gives that of the allyl bromide, and allyl bromide on treatment with that of the aqueous NaOH, which produces the allyl alcohol, and we know that the allyl alcohol has greater tendency for the allylic oxidation, so we get the allylic oxidation product, that is the alpha beta unsaturated carbonyl, and this alpha beta unsaturated carbonyl react with that of the lithium with the liquid ammonia in tertiary butanol, it will go to that of the cyclohexanone as the product. But in case of the metachlorobenzoic acid, it gives that of the epoxide as the product. The epoxide on cleavage is that of the BF3 etherate, and followed by the alkyl shift, it gives that of the aldehyde compound with the cyclopentane derivatives. Similarly, the selenium oxide is used for the allylic oxidation of the alkene to produces the allyl alcohol, which undergoes desmatic pyroidal oxidation followed by reduction gives the cyclohexanol. And another is that the KMNO4 is that of the produces the cis-diol intermediate, which on treatment with the sodium iodate it gives the dialdehyde compound. So the option 1A is the correct. Here the get question paper solution, get key answer, get paper key answer, key gives that of the wrong answer, where the C option is given, but this is not correct. Here the last step is the reducing step, so the reducing step is not go to that of the carbonyl compound, so the option C is not the correct in the key answer. So only one option, that is the A, is the correct option. Next is the carbene addition. Here the carbene addition has the 2-methoxynaphthalene on treatment with that of the carbene to give that of the propolone derivatives, and here the carbene is added with that of the alkene to give that of the cyclopropane intermediate, and this cyclopropane intermediate under cleavages to give that of the one derivatives, and this is the cycloheptanone derivatives. And similar problem is also taken from that of the Claydon group, where this is the carbene precursor on decarboxylation and gives that of the carbene intermediate, and this carbene intermediate can add with that of the dichlorocarbene, and after the cleavages to give the same type of the intermediate. This is the problem from that of the photochemistry, where the diphymethane rearrangement takes place, and this diphymethane rearrangement gives that of the, here the two radical is produces after the cleavage of this pi bond, and here the two here also another radicals, and these two radicals can added with each other and to produces the cyclopropane intermediate, which undergoes cleavages to give the that way cleavage, and give in that way the radical is come here and produces this radical, and this radical and these two radicals, these two biradicals, after rearranging to get this compound, this is the biradical, and this biradical after addition with the bridging molecule, bridging atom to get this product, and after rearranging we get that. So the intermediate involved in that, it must go through direct radical intermediate, it go through dipymethane rearrangement. Next is the problem of the ESR spectra, where the spin coupling with locals, where the different type of the protons is present here. First is the methylene proton, A type proton, and the hydroxyl proton is the B type proton. And on for A type proton hydrogen, the 2Ni plus 1, here I equal to half, and the methylene proton, number of methylene proton is equal to 2, and if plus 1 equal to, this becomes 3 lines. And for B type protons, for hydroxy proton, this becomes 2, and if we multiply it, then the number of hyper lines equal to 6. Similarly, different type of the organic problems is given here, where the different type of the hyper line spectra has been calculated. Suppose in case of the naphthalene system, here the two type of the protons, that is the alpha proton and the beta proton. If we calculated the alpha proton and the beta proton in their splitting, we get the, for alpha proton, higher number of lines equal to 5, for beta proton the number of equal to 5. If we multiply it, we get the 25 lines for the hyperline in ASR spectra. Next is the problem of the peptide synthesis, where the partial hydrolysis of the pentapeptide yield all possible tripeptide and dipeptide. The dipeptide that are obtained upon hydrolysis are given below, that is the val, Ella, and etc. If we rearrange these dipeptides in the following way, where the val, phenyl, valine, GLN, etc., and if we added in that way, that is the phenyl alanine is the terminal position and histidine is the terminal position, and the these are the, if we multiply, this is the pentapeptide formula, and this pentapeptide on partial hydrolysis, which contain the Ella is the subunit, are the phenyl valyl and valyl GLN, LAL GLN, etc., etc. So the number of tripeptide which contain the Ella is the subunits is the 3. Next is the stereochemistry problem, where the specific rotation of enantiomerically pure H2-butanol is plus 14. The specific rotation of enantiomer mixture of two asymmetric reduction of 2-butanone is found to be plus 7. Means if the two alcohol is present in the reaction mixture upon asymmetric hydrolysis reduction, it contains the two isomer. One is the R isomer, another is the S isomer. This is the enantiomer phase, so the hydride ion can attack in the top phase or in the bottom phase and we get the two isomers. If we calculated the optical purity of the enantiomeric mixture, this is the specific rotation of mixture by specific rotation in pure form. Here the specific rotation of the alcohol in the mixture is the 7, and the specific rotation of the pure form of alcohol is 14, and we get the 50%. And since the sign of the mixture of the alcohol is plus, and so the S content is the plus specific rotation, so the S isomer are the enantiomeric mixture which contain 50% S isomer, and so another 50% is the racemic mixture. So hence S isomer is the 75% and another remaining percent is that of the 25% R isomer. So the correct option is the 25% of R ethanol. Next is the problem of the hydroboration problem, where the thick-sile boron has been used for the hydroboration reaction, where the hydride ion is shifted to that of the terminal of the alkene system to give the alkyl boron compound, cyclic boron, and this alkyl boron has the vacant p orbital, so it can add to that of the carbon monoxide to that of the boron atom, and after the reaction and the cleavage of this boron epoxide to produces the gem diol intermediate, and it gives that of the carbonyl compound, and this carbonyl compound after the LDA and TMSCL treatment gives that of the protection of the enol intermediate, and then it can capture by the phenyl thiochloride to gives that of the SPH bond, and after the MC2B oxidation and heat gives the alpha beta unsaturated compound with the junction in the trans. So the option D is the correct. Next is the intramolecular Hague reaction problem, where the intermolecular Hague reaction means the oxidative addition takes place in presence of the palladium 0, and the palladium 0 undergoes oxidative addition to gives the palladium intermediate, and we get the alkene product. This is the Hague reaction, and after the Hague reaction followed by isomerization we get this indole derivative. So the option B is the correct. Next is the problem of the asymmetric reduction. Asymmetric aldol condensation. In asymmetric aldol condensation reactions, that is here the chiral auxiliary is attached to that of the carbonyl compound, and the Zimmermann-Traxel model has been operated here. In this Zimmermann-Traxel model, we get that the cyclic transition state where the chair-like transition state is present, and if this chair-like transition state is rearranged in that way, and we get that this is the question is that which phase, that is this is the enolate phase and this is the carbonyl phase. Here the enolate phase, in case of the enolate, the nucleophilic addition will occur from that of the top phase, and the carbonyl, the enolate is added to that of the bottom phase of the carbonyl, and we get the two type of the addition. One is the top phase of the enolate, another is the bottom phase of the carbonyl in the Zimmermann-Traxel model in the cyclic transition state, chair-like transition state. Here, if we arrange in the priority sequence as this becomes 1 and the methyl becomes 2 and the hydrogen becomes 3, and it is go to that of the clockwise direction, this is the 1 to 2 to 3 clockwise direction, and clockwise direction means it is the R phase, R-V phase, so it is the D phase. Here this is the bottom phase, and the carbonyl group is the 1 and alkyl group is the 2 and hydrogen is the 3, and this can be rotated in that way 1, 2, 2, 2, 3. This is also clockwise, but it is considered from the top, so it is becomes C phase, and so this is the C phase. So one is the D phase of the top, another is the C phase of the bottom. Next is that of the Hammett correlation. Hammett correlation is nothing but the substitution effect of the different type of the chemical organic reactions. In case of the organic reaction, this is the examples of the SN1 substitution reaction, and this is the example of the ester hydrolysis reaction. We know that ester hydrolysis is mainly facilitated for the BAC2 mechanism by the presence of the electron withdrawing group. Here the log Kx by Kh means the substituent effect of the Kx. If we use the electron withdrawing group, the ester hydrolysis of the reaction become faster. So in case of the S contain the chloride substituent, then the rate becomes more effective. So X become chloride, and in case of the in case of the P X equal to methyl, the rate becomes beta. But if the electron withdrawing it here, the in case of this is the SN1 reaction, if the electron withdrawing group is put here, then the SN1 reaction becomes slow. So if we put that of the electron withdrawing group, suppose R equal to X equal to nitro, then the rate becomes retard, so the slope becomes negative. And if we put that of the methyl group, the rate becomes highest, so X becomes methyl. And in case of the Q, the NO2 group has highest electron withdrawing compared to that of the CN, so it becomes middle. Hence the option. And in case of the T, X equal to OMe, if the T is put here, OMe is put, the ester hydrolysis rate becomes slower. So this option A and C is properly explain these two reactions. So the option A and C are correct. Next is the reagent chemistry problem. In this reagent chemistry problem, the conversion of that of the, this is the Ruppe rearrangement, where the Ruppe rearrangement is the lithium containing compound, acetyl halide compound, can add with that of the mercury, can add with the carbonyl, and followed by the mercury addition, and then the elimination of this alkene to produces the alpha beta unsaturated carbonyl compound. Similarly, in case of the C option, here the triplet group is generated from this amide substituent, and this triplet group can added with that of the Hague reaction. Here the electron donating group is present. We know that if the electron donating group is present, then the Hague reaction occurs with that of the alpha position compared to that of the beta position. And this is the vinyl ether, which on hydrolysis to give that of the alpha beta unsaturated carbonyl compound. Next is the problem of the rearrangement, where the rearrangement take place by the formation of the Wagner-Meruin type rearrangement, and the carbocation is produces the 3-degree type carbocation, and the methyl group is migrated, and the non-classical carbocation is produced the 3-center 2-electron non-classical carbocation, and we get this product, and the hydroxy substituent is present here, and we get the desired product. Here the option 1,2-methyl shifts, means this 1,2-methyl is shift here, and non-classical carbocation is also operated, and tertiary carbocation. So the correct option is the A, C, and D. Next is the pericyclic problem. Here the pericyclic reaction take place, means the methyl magnesium halide is added with that of the carbonyl compound and produces the 1,2 addition product, and this 1,2 addition product after the 1, 2, 3, this is the 1, 2, 3, 3 sigmatropic shift reaction will occur here, and here the hydrogen atom is absent, so the 3 sigma driving force for that of the 3 sigmatropic shift. So the after the 3 sigmatropic shift, the hydrogen atom is present there, and this CH bond is break down and to give the carbonyl compound, and then the correct option of that of the A and C, and this stereochemistry is not changed, so the ethyl group is present in the upside in the both case, but the methyl group and the hydrogenation reaction, after hydrogenation reaction, the hydrogen can go to that of the top side, or in the bottom side we get the two compound, and so the option A and C are correct. Next is the astomatic synthesis and yield calculations. In this case, the Kram's rule is taking here, and we get the two product. One is the major, another is the minor isomer, and if we convert it to that of the Fischer projection, and we see that this is the small side, so this methyl group is attacked in that side, we get the alcohol, and this is the alcohol, and this small side attacked is the preferable, and this is the major one, and this is the minor isomer. The problem is that in the following reaction, 13.4 gram of aldehyde P gives diastereomeric mixture of 2 and R in the ratio 2:1. If the yield of the reaction is 80%, means 13.4 gram of P means how many moles of the P? Means this is the reactant, 0.1 mole of reactant. So 0.1 mole of reactant is converted to 80% product. So this is the 0.08 mole product, and if we divide it in the 2:1 ratio, we get the one isomer is the 0.052 mole, and two isomer becomes 0.052 mole, and this 0.5 mole, if the molecular weight is multiplied it, we get that 7.92 gram of the desired product. Thank you for the watching of this video.